Hello and welcome to our February webinar. Today we'll be talking about high performance ventilation with our presenter Nick Young from the Association of Energy Affordability. My name is Matthew Mills. I'm an energy advisor for the Multifamily Energy Program, and I will be hosting the webinar and taking questions. We are using GoToWebinar for today's presentation, and a few housekeeping notes and instructions on how to use GoToWebinar before we start. Today's webinar will be recorded and available on the program website within a few days. Currently, all attendees are in listen-only mode. So if you'd like to ask a question, please use the questions box in the GoToWebinar panel, and I'll do my best to sort and answer the questions in the order that they're received. And at the end of the presentation, we'll open up the audio line for questions. So in order to participate in that discussion, please enter your audio pin, which is located on the center panel of your screen, and then raise your hand in the meeting panel and I can unmute you and you can talk. So if you haven't already, a good place to hear about our upcoming webinars is through our monthly newsletter. So I encourage you to register for that, and we send out either tips or program updates, as well as all trainings and webinars that are currently scheduled. We have a little bit of a break after this one, but keep an eye out on that webinar or that newsletter as it comes out, and you'll be alerted to any new opportunities coming up. So a bit about the trainer. If you haven't attended one of these webinars yet, Nick Young is our trainer from the Association for Energy Affordability, and he does a great job bringing insight into all of the various topics that we deliver. So as a trainer, Nick enjoys helping demystify technical concepts and giving people the tools and confidence to use different approaches that can improve buildings and reduce environmental impacts. He firmly believes that strategies to address the housing and climate crisis are complementary and not competing. AEA, Association for Energy Affordability, is dedicated to preserving safe, healthy, and affordable housing and reducing climate impacts through energy efficiency and building decarbonization. They are very happy to partner with programs like ORMEP that share those similar goals. So as a reminder why we're hosting these webinars is that OHCS's multifamily energy program provides incentives for energy efficiency measures that result in electric savings. So if you worked with our program and you submitted an energy efficiency plan, you can see that those savings can come from a variety of different measures, many of which have been covered in past webinars and presentations, which are available on the program website, as I said before. So if you're curious, check that out. But today we're specifically focusing on savings that can come from high performance ventilation. And this is an increasing popular topic as building envelopes become tighter, you need a different ventilation strategies. So that's why we're hosting this webinar, and there's lots of interesting information that Nick will be presenting, and I'll hand it over to Nick now so you can take it away.
Awesome, thanks Matthew. Is my audio okay?
Yeah, you sound great.
Okay, awesome. Okay, so quickly go through the agenda today. We're going to start with some basics of ventilation and discuss sort of from oldest and simplest to more modern and more high performance ventilation systems, starting with natural ventilation, exhaust ventilation, balanced ventilation, and then wrap up. Matthew's actually going to share with us some ventilation case studies from the ORMEP program. So let's start off with some basics of ventilation. And frankly, ventilation is a tricky subject, particularly for folks who work in affordable multifamily, because we've all been into existing multifamily buildings with all kinds of ventilation systems. These buildings might be underventilated. They might be overventilated. It could be erratically ventilated. Sometimes it's well ventilated, sometimes it's not. Maybe it's intermittently ventilated. Sometimes the fan turns on and then turns off. Maybe it's on a timer or some other thing, or who knows why it happens. And the truth is that very few existing multifamily buildings, particularly older buildings, have effective balanced ventilation systems. And in this training, we'll discuss ways to avoid these problems in your projects and deliver consistent, controlled ventilation. So what's the point of ventilation in the first place? Well, one of the primary purposes is to remove air pollutants from inside. That includes things like carbon monoxide, or CO, which is a byproduct of incomplete combustion. Carbon dioxide, or CO2, that is what we breathe out. But if there's too much CO2, we can feel lightheaded, there's not enough oxygen, so we need to get rid of that too. VOCs, or volatile organic compounds, these are things that are in like glues and building materials and solvents, and they are not good for you. Particulates also. So there's this term PM2.5. PM stands for particulate matter, and 2.5 means 2.5 micrometers and smaller. And PM2.5 particulates are particularly bad for human health. These can come from things like cooking, dust, or even outdoors. For example, if a building is near a highway, and auto exhaust contains a lot of PM2.5. Just to give you a sense, a human hair is 70 micrometers in diameter, and we're talking about particles that are 2.5 micrometers. So it's about 30 times smaller than the diameter of a human hair. So very, very, very small, and because they're so small, they can sort of get into they can get into your bloodstream and into your body more easily. Also, things like tobacco smoke, we want to remove those if that's in our building, and potentially radon, depending on where the building is located. There may be sources of radon in the ground, and we want to get those out of the building. In addition to these air pollutants, we also want to remove moisture from our buildings oftentimes. Moisture can come from things like baths, showers, cooking generates significant moisture, as well as people. As we all know, when we've been in an indoor space with a lot of people and insufficient ventilation, it gets steamy, right? We're all breathing out, and that air that we breathe out has moisture. Moisture is evaporating from our skin, and so we want to try to not have excess moisture building up inside of our building, sort of regardless of where it's coming from. And then to balance this, we're taking all these other things out. What do we want to bring in? We want to bring in fresh, clean air. And it's really important. We're not just bringing in outdoor air. We want it to be fresh and clean. And so we're going to talk about ways to do that. So great ventilation really provides three things. It provides distribution. So it's delivering fresh air to the spaces where people are living. It provides filtration, so that fresh air and or the room air is continuously filtered. And we'll see some examples of how to do this through ventilation systems. And then finally, great ventilation provides balance, meaning that pressures in adjacent spaces are balanced. And we'll see examples of systems that provide some of these or all of these or a subset, and we'll sort of see how the different ventilation approaches stack up with respect to these ideas. Some key ventilation system characteristics. You'll hear a lot of terms thrown around when we're talking about ventilation, and it's important to just understand sort of what these terms mean. And you start with sort of like ways of describing a ventilation system. So first of all, you can ask yourself, are there fans in this building? If there are fans, then you have an active mechanical ventilation system. If there aren't fans bringing air in or out of the building, then you have passive or natural ventilation. So if you've got fans, you can then ask yourself, where are the fans blowing? If they're blowing air into the building, that's supply ventilation. If they're blowing air out of the building, that's exhaust ventilation. And if you have fans blowing in both directions, so you have one fan blowing in, one blowing out, that's balanced ventilation. You have both supply and exhaust. Third, when do the fans operate? If they operate all the time, that's referred to as continuous operation or continuous ventilation. And if they operate sometimes, but not all the time, maybe you can turn them on with a switch, or they're on a timer or some other sensor, that's referred to as intermittent ventilation. So like a kitchen range hood is a great example of a type of ventilation that's usually intermittent, right? You can choose to turn on the range hood or not. Next, what space does the fan serve? If it serves a single unit or a single apartment, that's usually referred to as individual or unitary ventilation. If it serves a stack of units in a building or an entire building or a whole floor, that's referred to as a central system. And finally, is there heat recovery in the system? If you don't know, the answer is probably no. But if there is heat recovery, you're going to have a more efficient system, and that's only really possible with balanced systems. If you don't have heat recovery, it's going to be less efficient, but it is more common. So if you're not sure if you have heat recovery, you probably don't. But we'll see examples of these as we go on, and you'll learn how to identify these types of systems and what the different characteristics are of them. Are there any questions that have come up thus far?
No, currently there are no questions.
Okay, let's keep on going and start with the oldest form of ventilation, which is natural ventilation. So natural ventilation means we have no mechanical ventilation. We have no fans. And so a building with natural ventilation relies on open windows or central shafts for airflow. Infiltration of air, so air comes into the apartments. You can see on this diagram, air is coming into the apartments and then up and out through this central stairwell with a skylight and a vented skylight up here. And this is all just based on pressures outside and temperatures and things like that. So there are some advantages to natural ventilation. One is that it's already there in older buildings. If you have a really old building with windows and no fans, like you've got natural ventilation. And it's low maintenance. There are no fans. You don't have equipment to maintain. Those are really the only advantages to natural ventilation. And there are many, many more disadvantages. So first of all, it's nearly impossible to deliver consistent flow rates because flow rates in a naturally ventilated building, one, they require people to open their windows. So if they don't open their windows, they don't get any ventilation. And then even if they do have their windows open, the flow rate is going to depend on there being a difference in pressure between inside and outside. If there's no difference in pressure or no difference in temperature, you'll get no airflow. And so I actually think, I wish we had, I would like to cross out the word natural here and really just call this random ventilation, because it's basically totally uncontrolled and not predictable in any way. So in addition to being difficult to control, it's uncomfortable for occupants. As we all know, when we've been in a building in the winter that has natural ventilation and it's cold outside, it either gets stuffy inside because you keep the windows closed, or you open the window to get some ventilation and then you have a draft and it's uncomfortable. So that's not good. The incoming air is unfiltered, right? We like to think of outdoor air as fresh and clean, but we've all been in places and experienced times when the outdoor air is not clean. Maybe you're a person with seasonal allergies and you'd really rather not have to open your window to get fresh air. Or maybe there are wildfires where you live, or you live in a building that is very close to a highway with a lot of pollution. There are pollutants in the outdoor air, and if we're just bringing in unfiltered outdoor air, we're not doing anything. We're just introducing those pollutants into the home. And the final disadvantage to natural ventilation is that it is no longer allowed in new buildings. You're not allowed to build buildings like this anymore. So really, we want to, as an industry, move away from natural ventilation and move toward methods of ventilation that are more controlled and deliver what we want, deliver distribution, deliver filtration, and deliver balance. So let's start moving in that direction. And the most common type of ventilation that most people are probably familiar with right now is exhaust ventilation. So exhaust-only ventilation typically is comprised of exhaust fans in the bathroom and the kitchen. These fans can be individual or central. So in this top illustration, we have an individual fan in each apartment that's being exhausted into a duct, and that duct is going out sidewall over here. So we have one fan per unit. So these would be individual exhaust fans. In the lower right image, we have a central shaft here with a rooftop fan, and each unit is exhausting into this central shaft. So that would be a central exhaust ventilation approach. So advantages to exhaust-only ventilation, relatively low first cost. People are used to doing this. This is often what is sort of assumed in a project budget because it's the cheapest way to meet minimum code for ventilation. There are, however, lots of disadvantages to exhaust-only ventilation that have negative impacts on our building. So first of all, many exhaust-only ventilation systems are noisy. And if they are noisy, people are likely to not use them. So a bath fan that's noisy might just not get turned on, right? We've probably all been in a bathroom. Maybe it's in an older building, or maybe it's in a newer building with a cheap fan, and the fan's really noisy. People are just not going to turn that on. That's especially the case for kitchen exhaust. Lots of people cite noise as a reason for not using their kitchen exhaust fan. So another disadvantage is that often, because this is the sort of lowest cost option, people specify very cheap equipment. And when you buy something that's cheap, it's more likely to fail prematurely. And so you may have more maintenance and upkeep costs or replacement costs. If it's poorly installed, you can get poor airflow. This is often something we see. With an exhaust-only ventilation system, so we're exhausting air out the top, but this apartment is going to maintain or reach some sort of equilibrium in pressure and flow from inside and outside. And so what goes out must come in from somewhere. But when you have exhaust-only ventilation, you're not controlling where the air is coming into the apartment. And even if you have an exhaust fan that's exhausting air, and then you have like a Z-duct, or you have a passive air inlet, people have done measurements of how much air is actually going in to that makeup air inlet, and it's not nearly as much as is going out your exhaust fan. So you may be getting some makeup air coming through that place that you think it's coming in, but there's a lot coming in from who knows where. Maybe it's from the apartment next door. Maybe it's from the apartment downstairs. Maybe it's through a crack in your window. Maybe it's through the wall, the socket, and coming through, from another unit. Who knows, right? We're not controlling where the makeup air is coming from. And because we're not controlling it, we're definitely not filtering it. Finally, this type of system has no heat recovery. We'll see what heat recovery is later, but when you don't have heat recovery, you have higher heating and cooling loads. And because this is the baseline, this is what people are used to doing, most people don't think about that. People don't think about this approach as having higher energy costs, but it really does versus an approach that we'll see later. So these are some of the challenges with exhaust-only ventilation. There are ways to do exhaust-only ventilation that make it, at least a little bit better than the sort of lowest cost bargain basement approach. So if you're going to do exhaust-only ventilation and you'd like to do at least a decent job of it, some things you can do. First of all, specify Energy Star fans. So what we have on the right is an Energy Star bathroom exhaust fan. These fans have to meet specific efficiency requirements. They have to that should be a greater than or equal to 2.8 CFM per watt, or less than 2.0 sones. Sones is a measure of noise. 2 sones, just for reference, is just louder than a whisper, which is why Panasonic calls their Energy Star bath fans the Whisper Green. So because they're quite quiet. A lot of these fans are also have other options. They can be adjustable speed, so you can dial in exactly the flow rate that the engineer has specified. Right? Ventilation is really a kind of a Goldilocks scenario. We don't want too much ventilation, and we don't want too little. We want kind of the just right amount of ventilation, and we rely on the mechanical engineer for our projects to specify ventilation flow rates. And we look to code to make sure we know what our flow rate is, and we don't want to go way above that, and we don't want to go way below that either. Some exhaust fans can have a delay timer, such that if someone turns it on, uses the bathroom, and turns it off, the fan will say, "Okay, cool. I see you've turned me off. I'm going to continue running for another 5 minutes or so," because often someone will come in, use the bathroom, and leave. And they may be in there for 30 seconds, a minute, but then, maybe we want the fan to run for a little bit longer to continue exhausting the bathroom for a bit. So you can have a delay timer. You can also have something like a humidistat, which is what we see, I believe, here on the right, and the lower right is an optional humidistat. So a lot of these fans have these optional sort of control packages that can come on them. And the humidistat actually senses humidity in the room, in the bathroom, and can turn on automatically. So if you are concerned that residents in your building may not operate or may not choose to operate the bath fans, you could specify them with a humidistat, and that way they would operate automatically, so you can ensure that you don't have any condensation issues. You can also put them on an occupancy sensor, so as soon as somebody walks in, they turn on. And finally, there are LED light kits. So often there's a bath fan light combo, and you can get LED light kits for them so that the lighting associated with this is efficient. But just one word of caution, that there are cheap Energy Star fans out there. I'll just say they are cheap because they are cheap. Talk to property management in your organization, see which fans they prefer and which ones they find themselves replacing constantly because they break. And try to find a way to specify quality fans that aren't going to break quickly. I'm not going to name any names, but there are cheap. If you're like, oh, we found an Energy Star fan for $40, you will get what you are paying for. Okay. So, I'm sorry. I should have shown this. Beware of bargain basement fans. Okay, so that was natural and exhaust-only ventilation. Are there any questions?
Yeah, there are. I have a question about how do you know what to set your CFM rate? Like you saw on the last slide.
Question.
Yeah.
So there should be codes in your state, probably referencing ASHRAE standards, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. They set standards for ventilation rates for indoor air quality for both residential and non-residential and multifamily buildings. I know California's mechanical code references ASHRAE standards, and I would assume Oregon's does too. So I would say check with the building department, check with your friendly local mechanical engineer, and they should know what the flow rates are.
Mm-hmm.
And it will vary by like the number of bathrooms. It may be sort of, you may try to balance it with like a whole unit ventilation requirement. So there are a few different parameters that kind of go into determining it. It's not just, it's definitely this much per bathroom. It sort of can vary, and so you should really check with a mechanical engineer or with your building inspector and make sure you're meeting the requirements in your local jurisdiction.
Yep, and I'll add on to that of if you're going through incentive offerings like ORMEP or other verification offerings like LEED or Earth Advantage in the Northwest, your energy consultant and verifier will be able to come in and actually check that all the fans are set correctly, which can have an impact on your tenants that move in.
Totally.
Mm-hmm. But yeah, that's it for questions for now. Thanks.
Okay, great. All right, so let's move on from natural and exhaust ventilation to balanced ventilation. And we'll start with the basic design principles for balanced ventilation. The basic idea is that we're going to start by supplying air to the living spaces. So in this case, supply air is represented by our blue duct here. So we're supplying air to the living space down here, to a bedroom up here, and to another bedroom up here. So that's the first piece. Then we're going to exhaust air from wet areas, so areas where we're generating moisture. So we're going to exhaust from a bathroom up here, from the kitchen up here, and from the laundry room down here. You can kind of see this register here from the laundry room. So we're supplying to the living areas. We're exhausting from wet areas like kitchen, bath, and laundry. And just a quick note on kitchen exhaust. So actually, let me back up a moment. Supply to the living areas, exhaust from wet areas, and we're generally going to be sending those two streams of air through a single unit, which we'll look more at on the next slide, but it's called a heat recovery ventilator or an energy recovery ventilator, an HRV or an ERV. And so one note, if you are using one of these systems, the kitchen exhaust cannot be coming directly from a range hood into the HRV. So often what people do is They may have a directly ducted kitchen range hood that they turn on when they're cooking, but that's it. And then they may have a kitchen area exhaust, so an exhaust opening somewhere not directly over the cooktop, but somewhere else in the kitchen that's connected to the HRV or the ERV. And what that does is that ensures that there is some amount of airflow coming through the kitchen all the time, even if people choose not to use their range hood, because no one uses their range hood every time they cook anything. Just nobody. Maybe professional chefs in professional kitchens do, because they are required to. But no one in their home turns on their range hood every time, right? And so we're always going to have cooking and moisture events happening in a kitchen. And so it's really useful to have an area exhaust in the kitchen. So that's the basic concept. You supply to the living spaces, you exhaust from your wet areas, and then you bring them both through this common system so that you can recover heat from the airstream. Let's talk a little bit more about what that looks like. So I'm actually going to start here with this diagram on the upper right. So an HRV or an ERV is, you could think of as represented by this this shape here in the middle. So let's say it's very cold outside, 0 degrees Fahrenheit. Rarely gets that cold where I live in the Bay Area, but it does some places in California and Oregon. So let's say it's 0 degrees outside and it's toasty 70 degrees inside. So we're bringing our 70-degree exhaust air into our HRV, and we're bringing our 0-degree supply air from outside, or fresh air rather, from outside into that same HRV. What's going to happen is these airstreams are going to pass through a heat exchanger, and they are going to exchange heat. So as this return air, or this extract air from the unit passes through the heat exchanger going this way, the fresh air is going to pass by it going this way. They're not going to touch. They're going to be on opposite sides of a heat exchanger, but they're going to exchange heat such that now this fresh air is going to get most of the heat from that 70-degree air, and it's going to come in at 65 degrees Fahrenheit. And that return air, or that exhaust air leaving the building, is going to give up most of its heat, and then we're only going to be exhausting air at about 5 degrees, or a little bit warmer than the fresh air we brought in, but not at 70 degrees. So you're conserving most of the energy that you're using for heating when we use a system like this. And it can work the same way in the opposite direction in the summer. You can keep the cooling inside and not bring in too much heat. So what we have with an HRV or an ERV is a single unit that provides supply and exhaust ventilation. The flow rates are balanced usually. Sometimes you're slightly pressurizing a unit, so you might be supplying 100 CFM and then exhausting 90 CFM, so you have slight pressurization to ensure that you're not pulling air in from somewhere else. Often these units will have MERV 8 or MERV 13 filtration on the supply air. So the air going into the unit, it's extra important to filter that because you're supplying that to your dwelling unit. There's usually a sort of a mild filter on the exhaust air too, and that's just to protect the heat exchanger from any dirt or dust from inside. And then the core of your HRV or your ERV is your heat recovery or your enthalpy recovery core, and that's where the airstreams are passing by each other and exchanging heat between each other. And there are a few advantages to an HRV or an ERV system. The first is that it offers the best available distribution, filtration, and balance. So those three things that we said are the characteristics of great ventilation systems. An HRV or an ERV is really the gold standard for delivering all three of those. Also, these systems reduce your heating costs because you're not just exhausting all of your heated air in the winter. They can also reduce cooling costs in the summer by not just exhausting all of that cool air and bringing in, hot air from outside. They also improve comfort, right? In the winter, the air coming into your apartment is no longer, in this case, 0 degrees, right? It's 65 degrees. And if the temperature difference is like 5 to 10 degrees from what it is inside, it's basically not noticeable. People don't notice that it's really that different. Finally, these systems operate continuously. And that continuous operation ensures that you get adequate ventilation even without the tenant understanding how the system works. So these largely do not require the tenant to have any idea how it works or to actively operate it in any way, which I think is great. It doesn't, natural ventilation, the tenant has to open a window to get any ventilation. A lot of bath fans, you have to turn it on. Some operate all the time, but sort of older ones you have to turn on. A system like this is designed to operate continuously. And so even if someone never touches it, they will always have a well-ventilated apartment. There are some disadvantages to a system like this. The first one, which is the one that gets most people, is they are higher first cost. So the equipment, the ducting, and the testing for these systems are going to cost more than your exhaust-only ventilation system that you may be used to specifying in your project. So that's real. And then also it has filters, and the filters need to be maintained and changed regularly. So that's something that needs to be factored into the operational cost and the operating budget for property management for properties that choose to install balanced ventilation systems like these. So I've sort of used HRV and ERV interchangeably thus far. So let's jump in a little bit and discuss the differences between an HRV and an ERV. So
Hey, Nick,
the full name, yeah? Oh,
you mind
yeah,
if we stop for a few questions real quick?
sure, of course.
Yeah. So the second one was actually about the filters, knowing that they have to be maintained and changed. But who do you see changing these filters in the in-unit HRVs?
Owners.
The owners.
That's who, yeah, projects that we've had that have chosen to install these, they have gone in with clear eyes and a commitment to changing the filters regularly.
Mm-hmm.
But
Yeah, and the
that is,
next,
and we've had other owners who are like, we don't want to do that. So if we do any HRV, we're going to do one on the roof, and it's going to be a central system. And we'll talk about sort of central versus in unit in a few slides.
mm-hmm. Yeah, I think that's a really good point. It's it needs to be acknowledged and written into the operations to have these things change, especially if they're in the units.
Totally.
Yeah, and the next one is, can you talk about the ducting for the HRV systems?
Yeah, I'll get to the ducting in a couple slides.
Okay, great. Then move along.
Okay. Yeah, these are great questions. Please keep them coming.
Mm-hmm.
So quickly about HRV versus ERV. So the full name for an HRV is a heat recovery ventilator. And the type of heat exchange that you get across the heat exchanger is sensible heat. And sensible heat is just the heat that we experience as a difference in temperature. The ideal application for this would be a building with high internal moisture gains where you're trying to get that moisture out of the building. And one thing to consider for an HRV is that it's going to have a condensate drain. So there's a bit of a blurry image. I'm sorry I don't have a higher resolution one. But this would be like a winter situation where outside it's cold and dry and inside it's warm and moist, and they want to remove some of that moisture. And so they are exhausting it, and then as this exhaust airstream cools down, it's condensing, and so you have to be able to drain that out so you don't get condensation in your heat exchanger. So that's the basic idea with an HRV. With an ERV, ERV stands officially it stands for enthalpy recovery ventilator, and enthalpy is just a fancy word for heat energy that includes moisture. Because these systems can exchange both sensible and latent heat. Latent heat is the heat of evaporation. So as we all know, when you have something very cold in a warm, moist environment, you're going to get condensation on that thing. So there's a certain amount of, so for example, if you're providing air conditioning in a climate where with a very hot and on a very hot and humid day, there's a certain amount of work that your air conditioner is going to have to do, first of all, just to remove moisture from the air. And there's another amount of work that it's going to have to do in order to actually cool down the air in terms of the temperature that we experience. So that temperature change is sensible heat, and that moisture change is latent heat. And what an ERV can do is it can actually exchange both. So where would you want an ERV? You'd want an ERV in climates with very cold winters or very humid summers. So basically the East Coast is a fantastic place to use an ERV, because in the winter, you can imagine, so this is a scenario, actually, if we look at this image, this is a scenario for a hot, humid summer day. So we've got fresh air from outside, imagine like Miami. Fresh air from outside, and it is 90% humidity, and you have nice, cool air from inside, but you need fresh air, but your inside air is not overly humid and it's cool. You don't want to bring in all this humidity, right? You don't want that coming into the building. So what you want to do is you want to exchange both heat and moisture so that the heat stays out and the moisture stays out, but you just get the fresh air. And that's what an ERV does. And it can work the other direction in the winter. You can imagine the left side would be inside, the right side would be outside. And if the outside is extremely cold and dry, and you've had to humidify to keep the inside of your building cold on a very cold, to keep the inside of your building comfortable on a very cold, dry day, you wouldn't want to then just exhaust all that humidity that you've added to the air. You want to keep it inside and keep the warmth and that humidity inside so you don't dry out your building. And so these are really great for those types of climates. So it's really, there's not like an easy, there are times when this is the obvious choice, an ERV, and then like when you do an HRV is kind of more of it can be a subjective choice. Also, we've had projects that are just like, we can't put a condensate line in because it doesn't fit wherever, constructability says that they can't do that. So then they go with an ERV because they just can't fit an HRV. They can't fit the condensate drain. So that's HRV versus ERV. There's another concept that's really important to understand, which is called bypass. And I strongly recommend anyone looking at an HRV or an ERV select a unit that has bypass. So what is bypass? If your unit has bypass, that means it can skip the heat exchanger. So in this case, we have intake air from extract air, supply air. Yeah. So we've got one airstream essentially that goes through the heat exchanger, but the other one doesn't. So for example, when inside it's 75 degrees and outside it's 65 degrees, you probably just want to bring in the outside air. You don't want to like keep all of your heat inside, right? And it'd be nice to have some of that 65-degree air. And this is a scenario that we experience a lot on the West Coast, right? It got a little warm during the day, cools off in the afternoon. Great. Let's just bring in outside air. We don't need it to go through a heat exchanger. We're not trying to keep our building 78 degrees. We'd like it maybe to cool down a little bit. We want to use our ventilation for some free cooling. So bypass is really good for shoulder seasons and cooler evenings. It can prevent overheating and reduce air conditioning usage and energy consumption. And it works like an economizer. If you're familiar with commercial HVAC units, this is essentially the same concept as an economizer. The thing is, though, a lot of cheaper HRV and ERV units do not come with this feature. And particularly if you're specifying an HRV or an ERV in a building without air conditioning, if you're just doing like electric heat and an HRV, you omit this feature at your own risk, because we're used to doing electric heat in buildings that had poor envelopes and were poorly insulated, had poor windows. When we then put just heating in a building with better insulation, better windows, better air sealing, now all of a sudden, if our building heats up during the day, it's not going to cool off nearly as quickly at night. And if you add on to that heat recovery ventilation that doesn't have bypass, you're just going to be keeping all of that heat inside. And people may be used to their apartment being a little bit warm in the late afternoon, early evening, but then cooling off overnight. You're going to end up with an apartment building that doesn't cool off very effectively overnight. And if you don't have air conditioning and you just have heating, because that's what sort of the paradigm is in your region, I would really just urge you to think twice about specifying an HRV or an ERV without bypass. Any questions on the last couple of slides?
Yeah, just on the bypass, how is the bypass controlled?
It's usually controlled on outdoor air temperature. So what you do is you specify a temperature range of outdoor air in which you want to just get that outdoor air straight in. So you could say, hey, HRV, ERV, when the outdoor air is between 60 and 75 degrees, just give me outdoor air. Don't put it through the heat exchanger. Just bring it straight in. This also will reduce your like fan power input because it uses less energy to move the air through the bypass. And there's just a damper that changes it. You know, you can select it. You can select whatever range you want. But that's the general idea.
Mm-hmm. Yeah, that's great.
Okay, so HRV, ERV controls, like I mentioned, they generally are set up to run continuously on a sort of low or standard setting. This ensures adequate ventilation, and there is no tenant understanding required. People don't need to understand anything about this, how this thing works. It just goes all the time. There is also usually a boost mode. And what this can do is temporarily boost the flow rate for showering and cooking. This can be controlled on a manual switch, on a carbon dioxide sensor, or on a relative humidity sensor. And if you think about how this system is working, what is it going to boost? It's going to boost everything, right? If we go back to our slide with the house, we can't just boost the kitchen or just boost the bathroom. We have to boost this whole unit. So when you hit boost in the, like let's say you have a boost button in the kitchen, it's gonna boost everything. And usually those are on a timer. So it might be, you could hit like a 10-minute boost or a 15-minute boost or something like that. So you can choose to use the boost feature if you want to. On a small apartment, you may not have, you know, all of these different outlets, so it may not have as much impact. But the key is that you're not just boosting one register, you're boosting the whole system. So you're maintaining balance in your building. You're not creating a pressure dynamic and sucking air in from the outside or pressurizing and blowing air out somewhere else. There also, a lot of these have something called party mode, which is a higher flow rate. It's almost like boost, but you like lock the boost. So you can imagine if you have a lot of people over, you want more ventilation, and you can set it to operate at a higher flow rate for a prolonged period of time. So there was a question about ductwork. On a very basic level, the two scenarios that are different are central versus in-unit HRV or ERV. So on the left, we have an example of a central system, and on the right, an in-unit system. For a central system, you're likely to have one HRV or ERV serving multiple units. So in this case, serving a stack of units. Sometimes it might serve a whole wing of a building. So you might have like runouts in the hallway for supply and exhaust. Sometimes these require fire smoke dampers that can add cost. It's really important to check with your local jurisdiction. Do you need a fire smoke damper just when the ducts penetrate a floor plate, or do you need one at every unit? So if the ducts are running through a hallway and then going into the unit, do you need a fire smoke damper there or not? We hear different answers from different jurisdictions. I was just dealing with this on a project the other day. The main advantage to a central scenario is that it's very easy to access and service the equipment, and it's very easy to change the filters, right? They're right there. For in-unit systems, like we see on the right, you have one HRV or ERV per dwelling unit. Sometimes these can be lower first cost than the central system because you don't have the sort of shafts and you don't have the ductwork. Sometimes these involve running ductwork up and down hallways and then up a shaft. And so these can sort of, because you have less sheet metal work, sometimes these can be less expensive. But, you know, I would encourage folks who are looking into balanced ventilation to price both and not just assume one is going to be cheaper than the other one. And, you know, even if, you know, your MEP says, your mechanical engineer says, oh, that one's definitely cheaper, you know, do your due diligence. Let's actually go through this exercise and let's price this out and let's see and let's get a real bid, because sometimes we've had projects that have been surprised at like, oh, we were really expecting this one to come out more, but it's the other one that's cheaper, and like, okay, great. Like I've had projects where Central came out cheaper and the owner was thrilled because Central means that they can deal with changing the filters more easily, and that was like their main concern. So yeah, so in unit could be lower cost, but you should confirm, and then you have to enter the units to maintain the filters, or you have to really roll the dice and rely on tenants to maintain the filters, which I do not recommend. But maybe you have super engaged tenants, and you can just leave the filters at their door and a little note, and they'll change them. Who knows? Who am I to say? People don't have tenants who could do that. But that has been a challenge for some projects. Once you're in the unit, so like once you're sort of here or you're here, then the ductwork looks like what we saw on that first image. You're going to be supplying air into usually the bedroom and the living room, and you're going to be exhausting air, sometimes just from the bathroom, sometimes from the bathroom and the kitchen. Different projects do it in different ways. But that's the basic idea. So the overall winners for ventilation systems in terms of delivering distribution, filtration, and balance is really the ducted HRV, ERV. It wins in all categories but first cost. One thing to think about and to talk with your mechanical engineer about and your energy consultant is, could having an HRV or an ERV allow the project to save costs by downsizing our heating or cooling systems, right? Like if we specify, like maybe we were really concerned about overheating and we were going to put in an air conditioning system, but if we specify an HRV with bypass, maybe that's good enough and we don't need air conditioning, or maybe the HRV reduces our heating loads sufficiently in the winter that now we can specify a smaller heating system. So that's something to think about. I would say second place would be other balanced systems or Energy Star exhaust fans with continuously operating fans. Those can deliver better than a lot of existing buildings. So it's a better solution than just sort of meeting code minimum. So that's the basics of these ventilation system types. Now Matthew's going to talk us through a couple of ventilation case studies.
Yeah, thank you, Nick. Yeah, as Nick just said, I just wanted to talk through a few case studies of projects I have personally worked on that have integrated high-performance ventilation strategies. So the first one is coming from the developer Pacific Crest Affordable Housing, is located in Central Oregon. And their upcoming project, Canal Commons, is a 48-unit new construction project right in the center of Bend. And Pacific Crest really prioritizes efficient design, but and then getting the maximum results for their future tenants. So they wanted to put in this central ERV unit, this GreenHEC ERV. There's two different buildings, so there's one central ERV system for each of those buildings. But this is their way of delivering fresh, filtered, and tempered air to each of the units and common areas. And they've noticed an impact on past projects. Their Azimuth 315 project also installed these GreenHEC ERVs and then polled tenants to ask them about the change in air quality. And they had noticeable responses of healthier, less sick days, things like that. And they're very happy with these systems and continually are going to be putting them to their projects. And as
Awesome.
Nick mentioned in the past, these systems help with offsetting some of the heating and cooling costs. So through the whole building pass and the energy modeling for this project, they were able to estimate about 12,500 kilowatt hours in savings. And so this next one, and I wanted to show this as a compare and contrast, since the last project, Canal Commons, used a central ERV system. I have also worked with Reach CDC on their Mary Ann project, which is using the other kind of system, the in-unit HRV installation. So this 54-unit new construction project in Beaverton is using the ALLS H110 HRV system. And each unit has an individual HRV installed in it. And the HRV is actually installed in the ceiling above each unit, well, I suppose between floors. Um, and it's running its exhaust, as we talked about, from the bathroom, and then it's exiting all of that through the walls. So it's pretty minimal design, but it has a great impact on the ventilation of the whole building. Some of the things that contribute to it is that the Mary Ann has a really aggressive building tightness goal. So they're targeting a 1.3 ACH 50, which is pretty significant, and that comes through pressurizing the units and doing diagnostic testing. But when you get that tight in your construction, you really want to integrate a high performance ventilation system. And so they have put in this dedicated balanced ventilation for each of the units to make sure they're getting enough air, and then allowing it to be filtered and all that. A next thing that played into it partially, but I did want to hit on, is that odor control. Since each of these units is going to be individually ventilated and filtered, you don't really have to worry about smells or any other gases coming from neighboring units. Each unit is going to be self-contained, and that definitely impacts occupant satisfaction of living in the unit. And then this one as well, with the benefits from savings from heating and cooling costs. So they were able to project out 21,000 kilowatt hours in savings through the energy modeling of the whole building pathway. So it's just a couple examples of projects that I'm currently working with that's coming through the ORMEP program that really have benefited from considering high performance ventilation and putting in either an HRV or an ERV centrally or in unit. And if you have any questions about this or the systems or how they did it, please feel free to reach out, and I'm happy to offer my guidance or get you connected.
Yeah, that's awesome. One thing I noticed on here, Matthew, is if we look at the top view where it shows the four openings for the ducts, notice that it's just showing a 4-inch diameter duct. So when we're thinking about the ductwork for these HRV, ERV systems, we're not talking about the huge, like 8, 10-inch ducts that we're used to seeing for heating and cooling systems. These are much smaller ducts, so it's much easier to run them sort of through the ceiling or through a wall or something. We're not dealing with gigantic ducts that are really challenging to run, because this is just for ventilation air. And the amount of air that you need to move for ventilation for fresh air is much less than what you'd need to move for, say, heating and cooling in a traditional heating and cooling system. That's just something to keep in mind, is the duct size is going to be smaller for one of these systems than for like a ducted heating and cooling system.
Yeah, that's a great point.
So I think that pretty much does it for our webinar today. Any other questions that have popped up?
I don't see any questions or hands raised for the moment, but we can hang out for a couple more minutes and see if anything comes in. But yeah, otherwise, thank you, Nick. I think it was really interesting. I think you did a great job of presenting. And I hope we see more HRV systems and balanced ventilation strategies integrated into our projects.
Awesome. Yeah, that sounds great. Thanks, Matthew.
Yep, so I'm not seeing anything. So if you have any comments or questions post webinar, please feel free to reach out to myself or Nick Young at the email you see on the screen.